Hi students, I will try in this educational video to implement an academic example showing how material elasticity can be applied in order to evaluate the mechanical resistance of a cylindrical shell subjected to a certain external loading. Okay, let's go. Well, as you can see in this figure, a cylindrical shell is considered. It can be a tank or a pipe. And you can notice that this cylindrical shell is made of a material characterized by a certain number of mechanical properties, which are the Young modulus E, the Poisson's coefficient nu, and the yield strength sigma E. This cylindrical shell is subjected to an external loading. We have an internal uniform pressure Pi applied on the internal surface of the shell. We have also an external uniform pressure PE applied on the external surface of the shell, and also we have a tensile sigma applied on the basis of the shell. It's to note here that the height of the shell is considered infinite. Now I will consider a point M in this shell and I will try to determine the form of the displacement vector or the displacement field in this point. The general form of the displacement field denoted by the vector u defined at the considered point M will have three components in the cylindrical base. UR is the component along the radial direction ER. U theta is the component along the circumferential direction E theta. And UZ is the component along the longitudinal direction EZ. The considered point M in the cylindrical base will have three coordinates. R is the coordinate of the point M along the radial direction ER, and theta is the coordinate of the point M along the circumferential direction E theta, and Z is the coordinate of the considered point M along the longitudinal direction EZ. Now, based on the geometric symmetry, which is a cylindrical symmetry, and also based on the loading symmetry, we will simplify this general form of the displacement field. Now, when we examine the loading symmetry applied on this shell cylindrical symmetry, we notice that the uniform pressures, internal or external, will induce only a point displacement along the radial direction. Also, this tensile stress will induce only a displacement of points along the longitudinal direction. So, under this stress state or under this loading, pressures and tensile, only the radial displacement and also the longitudinal displacement, so UR and UZ, are allowed. We have no circumferential displacement U theta. It is to note also that for the radial displacement UR, the points having the same r, in other terms, the points having the same radial coordinates will have the same radial displacement even if they have no or they have different circumferential coordinates theta and longitudinal coordinates z. The displacement or the radial displacement ur will depend only on the radial position of the point. It does not depend on the circumferential and the longitudinal coordinates of the point. So ur depends only on r. Now for the longitudinal displacement uz, it's to note that the points having the same longitudinal coordinates z will have the same longitudinal displacement uz, even if they have different radial coordinates and different circumferential coordinates. So the longitudinal displacement uz will depend only on z. The general form of the displacement field is then simplified into this form, which show that the displacement field has only two components, a component along the radial direction, which is ur, and a component along the longitudinal direction, which is uz. The circumferential component u theta is equal to 0. Also, the radial component ur will depend only on the radial coordinate of the considered point M, while the longitudinal component will depend only on the longitudinal coordinate of the considered point M. Now, based on the form of the displacement field, we will determine the form of the deformation field, of course, at the considered point M. The deformation field is characterized by its linearized deformation tensor epsilon. The tensor epsilon is given as 1/2 the sum of the gradient displacement tensor and the transpose of this gradient displacement tensor. Of course, the gradient is applied in the cylindrical base. We obtain then the form of this linearized deformation tensor epsilon, and as you see, it's a diagonal tensor, of course defined in the cylindrical base er, e theta, and ez, and the normal strain along the radial direction is given by the variation of the radial displacement with regard to r, and the normal strain along E theta is given by the radial displacement divided by the radial position r, and the normal strain along the longitudinal direction is given by the variation of the longitudinal displacement uz with regard to z. Of course, this linearized deformation tensor epsilon is defined in the considered point M, so r here and z here represent the radial position and the longitudinal position of the considered point M. Knowing the form of the linearized deformation tensor epsilon, we can obtain the form, or we can determine the form of the stress tensor using this constitutive equation relating the stress to the deformation fields. Here mu and lambda represents the coefficients of Lamé, and TR means the trace, so it's the trace of the linearized deformation tensor epsilon, and I represents the identity tensor. And as you see, the form of the stress tensor is a diagonal tensor, so we have only normal stresses. So we have the normal stress along the direction ER, E theta, and EZ. Here, T represents or means the trace of epsilon. So the trace is the sum of the diagonal terms of a tensor. So T here, as you see, is the sum of the diagonal terms of the linearized deformation tensor. Now, it's to note that this constitutive equation relating the stress field or the stress state to the deformation state is only applicable when epsilon is kinematically admissible. Only on this case, the stress tensor sigma can be obtained from or based on the deformation tensor epsilon. One way to verify that the tensor epsilon is kinematically admissible is to use this compatibility equation. Epsilon is considered kinematically admissible if it verifies this compatibility equation, which states that the gradient of the divergence of the tensor epsilon plus the transpose of the gradient of the divergence of epsilon minus the gradient of the trace of epsilon minus Laplacian of epsilon must be equal to 0. The tensor is 0. It's to note here that in our case, in our example, it's not necessary to check that the linearized deformation tensor epsilon verifies the compatibility equation in order to state that epsilon is kinematically admissible. Why? Because we know exactly the form of the displacement vector which gives the tensor epsilon. Since we know the form of the displacement vector, so necessarily the linearized deformation tensor epsilon will be kinematically admissible. It is to note also that the stress tensor, the sigma tensor, should be statically admissible. And this static admissibility is verified when the stress tensor sigma verifies the equilibrium equation, which states that the divergence of the stress tensor sigma plus the density of the material constituting the shell multiplied by the specific forces applied at a distance defined by the vector F, this kind of forces like the gravitational acceleration, minus the acceleration of the shell defined by the vector gamma should be equal to the vector 0. Now, if we consider that these forces, the forces applied at a distance, are negligible, and if we consider that the shell is motionless, so gamma is equal to the vector 0, we will have divergence of the stress tensor sigma must be equal to the vector 0, which is our case since our domain, our shell is in equilibrium, so the vector gamma is equal to the vector 0, and also the distant forces are neglected. So the divergence of sigma will be equal to the vector 0. Also, it should be remembered here that the divergence is applied in the cylindrical base, and also the divergence of a tensor of order 2, which is a matrix, the tensor sigma, will give a tensor of order 1, which is a vector. So the vector is equal to 0 means that all the components here or the vector are equal to 0. And you can notice here that the second component of the vector, which is the component along the direction e theta, is a trivial equation. Why? Because sigma theta theta depends only on r, which is the radial position of the considered point M, and z, which is the longitudinal direction of the considered point M. So sigma theta theta does not depend on theta. So the variation of sigma theta theta with regard to theta will be equal to 0. So the second component of the vector gives a trivial equation. So the system of the three equations given by divergence of sigma is equal to the vector 0 will be simplified into these two equations. Now, if we replace the normal stresses sigma rr, sigma theta theta, and sigma zz with their expressions in function of ur and uz, which are the radial component and the longitudinal component of the displacement field, we obtain these two differential equations in function of ur and uz. The solving of the two differential equations gives the radial and the longitudinal components ur and uz of the displacement field in function of alpha, beta, gamma, and delta, which are constants of integration determined based on boundary conditions. Injecting these expressions of ur and uz in the expressions of the normal stresses sigma rr, sigma theta theta, and sigma zz will give the expressions of the normal stresses in functions of capital A, capital B, and capital C. Of course, here R represents the radial coordinate of the considered point M. And the capital letters A, B, and C are related to the constants of integration alpha, beta, and gamma as it is expressed by these formula. It should be remembered here that lambda and mu represents the Lamé coefficients, and here E and nu represents the Young modulus and the Poisson's coefficient respectively. It is to note here that the constant of integration delta does not appear in these formula. Why? Because this constant delta represents a non-deformable solid displacement along the longitudinal direction of the shell. Mathematically, it will disappear during the derivation of the longitudinal displacement uz. Now, taking into account the boundary conditions, which can be summarized as an internal uniform pressure Pi applied on the inner surface of the shell defined by its internal radius Ri, and an external uniform pressure Pe applied on the external surface of the shell defined by its external radius Re, and also a tensile stress sigma applied on the basis of the shell. We obtain the constants capital A, capital B, and capital C in function of Pi, Pe, Ri, Re, and sigma. Inserting these constants A, B, and C in the normal stresses sigma RR, sigma theta theta, and sigma ZZ, we can obtain the stress tensor sigma. Also, inserting the constants A, B, and C in the constants alpha, beta, and gamma will permit to obtain the radial displacement UR and the longitudinal displacement UZ, which will permit finally to obtain the linearized deformation tensor epsilon. Now, since we have all the components of the stress tensor sigma, of course, in function of Pi, Pe, Ri, and Re, and sigma, we can apply the von Mises yield criterion in order to obtain the equivalent von Mises stress and compare it to the yield strength. If we consider that the internal uniform pressure is higher than the external uniform pressure, the most unfavorable case in terms of elasticity, of course, will be obtained for the points located in the inner surface of the shell. So for the points located at the radial position R equal to Ri. Then if we inject Ri in this R, in this inequation, in the place of this small r, we will obtain this inequation. Finally, if we know the numerical values of the internal pressure Pi, the external pressure Pe, the internal radius Ri, the external radius Re, and also the numerical value of the tensile sigma, and the numerical value of the yield strength of the material constituting the shell, this yield strength, sigma E, we can check whether or not the shell will remain in the elastic domain. That's all for this educational video. If you have any questions or any remarks or any suggestions, don't hesitate to mention it in the comments. Great students, please accept my deep respects.